Chapter 3, Part 5, Cycloalkanes, Nomenclature of Cycloalkanes, and cis-trans isomerism. Cycloalkanes are exactly what they sound like. They are alkanes that are cyclic. A ring has been formed in order to make these. It's important to note that cycloalkanes have 1 degree of unsaturation. So these are not technically saturated alkanes, even though they don't have any double bonds or triple bonds. And the reason why is if you look at cyclopropane, for example, there are 3 carbons in cyclopropane and 6 total hydrogens. Let's doodle all those on real fast. But if you look at propane, which is a saturated alkane, you have 3 carbons and 8 total hydrogens. So this is the number of hydrogens you would have if you were fully saturated. So there's 1 degree of unsaturation in order to form a ring. And you can kind of see that if you look at how a ring would be formed. So in order for a bond to form between these 2 carbons, for example, we would have to lose these 2 hydrogens in order to make that make sense. So that's where that degree of unsaturation comes from. Looking at just general nomenclature, all you do is count up your carbons in the ring, 1, 2, 3, use that prefix, and then everything else that we've seen before, an infix, tells us that there are only carbon-carbon single bonds, E suffix tells us it's a hydrocarbon, and then cyclo tells us that it is cyclic. When students are naming cycloalkanes, I think the number 1 thing that I see missing from the name is cyclo. So a 4-membered ring is called cyclobutane. A 5-membered ring is called cyclopentane. A 6-membered ring, cyclohexane. 7 members is cycloheptane, and 8 members is cyclooctane. You could continue from there, but I figured I didn't need to continue to demonstrate this point. Something else that's important to note about these rings is that some of these rings are being forced outside of normal bond angles. These are all sp3 hybridized carbons. We can tell that because they're all single bonds. So we know that they're sp3 hybridized, but in order to make a 3-membered ring like this, we are taking our normal 109.5 degree bond angle and forcing it into a 60 degree bond angle. This is going to put a force on the ring that's called ring strain. And this is from just forcing something to be too small or also too big. Cyclobutane is forcing 90 degree angles. Now, it is important to note that none of these molecules are actually flat the way they look on the paper. Cyclopropane is flat. There's no other alternative. All 3 of these carbon atoms are in the same plane. But cyclobutane, because of this ring strain, is going to form a different kind of structure where you end up kind of creating this fold in the molecule. And that allows the bond angles to be a little relieved. Cyclopentane does the same thing as well, where instead of existing as a flat molecule, if we were actually to look at it in 3D, I'm going to draw a kind of a side angle, what we would see is that one of the carbons is kind of popped out of plane. This is called the envelope conformation, and this allows the cyclopentane to have slightly more open bond angles. Now, cyclohexane is just an instance of perfection. All the bond angles are exactly 109.5 degrees, and this is because of something called the chair conformation, which we have entire slides about in this slideshow, so we're not going to talk about it right now. Cycloheptane and cyclooctane kind of have the opposite problem of our smaller rings, where we are forcing larger bond angles than appropriate, and so that's a different type of ring strain, and it's a little less severe potentially. When it comes to ring sizes, a 6-membered ring is always going to be favored. And then from there, typically a 5-membered ring and then a 7-membered ring are the ones that are more likely to form in a ring forming reaction. When we are naming cycloalkanes, we end up using pretty much the same IUPAC rules that we've been using for our linear straight chain alkanes. We just have to add in a couple extra things. So you use your IUPAC prefix to indicate the number of carbons in the ring, and you add cyclo to the beginning of that parent chain name that we've learned. So that's where we get cyclopentane, cyclohexane, etc. If the ring has substituents, it starts getting a little more complicated. If there's one substituent on the ring, you add the substituent name to the beginning, so something like methyl cyclohexane. If there are multiple substituents, you're going to have to put numbers on the ring. And the rules that we're going to use are here, and then we're going to do some examples. So you number the ring so that the substituents have the lowest possible numbers. You can also end up with potentially more than one numbering system. And in that case, you use alphabetical order in order to decide where to start. So the group that has the earliest letter in the alphabet of the two potential starting places would end up being where you start. And then you list substituents in alphabetical order, just like you do with our straight chain alkanes with the locants before the name of the ring. So let's practice naming some cycloalkanes. Go ahead and pause this for yourself and try it on your own. You might surprise yourself. So for this first example, this is a 5-membered ring. And because we only have one substituent on the ring, we do not have to provide a number for that substituent because no matter what, we would always number it number 1. So we don't need to call this 1-methylcyclopentane because that's just kind of redundant. The name of this molecule is just going to be methylcyclopentane. And as I mentioned before, the most common mistake that I see with students naming cyclic alkanes is leaving off that cyclo. So make sure that you always provide a name that fully describes the molecule. On the next one, we have a choice between starting our numbering at ethyl or methyl. Our numbering system would be the same no matter which way we went. It would either be 1 and 3 or 1 and 3. This is an example of when you have to use the alphabet in order to decide where to start numbering. Ethyl comes before methyl alphabetically. So this is carbon number 1, 2, 3, 4, 5, 6. And we're just going to number around the ring in the direction that gives us the lowest possible numbers. We wouldn't number it this way because we would end up with a numbering system that was 1, 5 rather than 1, 3. So the name of this molecule is 1 ethyl 3 methyl cyclohexane. For the next molecule, there's only one place that you could start that would give you the lowest overall numbering scheme. So that's where we have to start. Starting here and going counterclockwise gives us our best possible numbering scheme. So this is a 7-membered ring. We have substituents on carbons 1, 2, and 4. Number 4 is an ethyl, and on carbons 1 and 2, we have 2 methyls. So that's going to mean that we have to use dimethyl in our nomenclature. So ethyl comes first alphabetically. So our name is 4-ethyl 1, 2 dimethyl cycloheptane. So I'm using the hept prefix because we have 7 carbons in our ring. Don't forget that cyclo, and don't forget di. Working with cycloalkanes brings us into our first situation where the 3D shape of molecules is actually really important. So let's take a look at this example, 1,2-dimethyl cyclohexane. This molecule has 2 methyl groups spaced 1 carbon apart. Now every molecule that we've looked at so far has been drawn flat, but that's not how this molecule actually exists. This molecule is 3D, and there are 2 different possibilities for how these methyl groups could be positioned. Remember, there is a methyl and a hydrogen on every single one of these 2 carbons. And then there are hydrogens all the way around the ring that we don't need to draw. But because we have these 2 different groups here, the direction that the methyl group is pointing actually matters. So One option would be for the methyl groups to point in the same direction. They can either be both up on wedges coming at us or both down from us on dashed wedges going away from us. And that would be called cis. Or we could have the methyl groups going in opposite directions, one going up above the ring and one going down below the ring. And this would give us two different options. These two molecules are actually different from each other, even though it's kind of maybe hard to discern why. That's actually the topic of chapter 6, so we don't need to spend a lot of time on that right now. But we do need to know that there is this option of cis and trans. And because these are molecules that have different properties, they could have wildly different melting points and boiling points. We actually have to be pretty specific about their names. So this is cis 1,2-dimethyl cyclohexane, and these two are both called trans 1,2-dimethyl cyclohexane. And when we get to chapter 6, we will learn a way to actually distinguish these two through nomenclature as well. And just to be clear, cis means both substituents are either up or both down. They must be on the same face of the ring. This terminology, face of the ring, means same side of the ring. Trans means the two substituents are pointing in opposite directions, on opposite faces of the ring.